Okay, all right. Yeah, so welcome to Qiskit Fall Fest. It's for the computing workshop. And today we'll run from 1:30 to 6:30 p.m. And so here's the schedule. You probably already see on the GitHub. So we'll first begin with 2 1-hour lectures. So I will talk about introduction to quantum computing basics, unfortunately in English. And Juan will talk about quantum computing algorithms such as teleportation algorithm in the next hour. And then we'll take a 1 and 40 minutes lunch break. Then we'll come back to work on quantum challenges, which is basically 2-hour problem solving. And then after that, we will discuss on the problems that we solve. And for some 45 minutes, and we'll maybe Jian will give a research talk in quantum computing with emphasis on physics. So some additional information about our event. So you will be doing problem solving on three quantum computing problems using Qiskit languages, and the personal computer is required to participate in the challenge. So and it's okay to ask help from the mentors, all of us at any given time, but it's not allowed to collaborate on by solving the problem. And the best score will be notified by us, and they'll be given a special prize provided by IBM Quantum team directly. And we'll also send an optional survey email after the event. And please provide your feedback, and we hope to hold similar event in the future. Okay, so I'll begin my lecture with introduction to quantum computing. So this is my table of content. The first part, I will do some introduction to quantum computing, and then I will talk about the quantum computing basics, introducing the mathematical notations. And then I'll talk about the Qiskit, which is nowadays the predominant open source quantum computing framework. And in the end, I will summarize by pointing some directions in quantum computing in the future. So we have seen a lot of developing quantum computing for the past 40 years, ever since Richard Feynman proposed the quantum computer in 1981. So we were able to build the coupling gate and then develop, you probably know, the Shor's algorithm. And then we have some hardware developed in error correction. And then more recently, we have seen a very promising feature that is a variational quantum eigensolver used widely in chemistry. And recently, we have also seen quantum computing merge with machine learning. So you have the quantum machine learning. But currently, we're still in a noisy intermediate scale quanta, the NISQ era, where quantum bits or qubits and quantum operations are substantially imperfect. However, as you can see here, there are a lot of companies, Google, IBM, Intel, IonQ, that developing different hardwares using different physical system. And there have been a lot of software as well from Qiskit, Cirq, and so forth. So we are gradually towards a era of quantum advantage in the future, hopefully in the next 10 to 20 years. So quantum advantage is defined as a purpose-specific computation that involves a quantum device that cannot be performed classically with the same reasonable amount of time and energy resources. So there have been already some preliminary quantum advantage applications, such as sampling pseudo-random quantum circuit with 53 bits using the Google Sycamore programmable chip. So it's a superconducting chip. And there are also some photonic quantum computer developed for another physical problem, a Gaussian boson sampling. And more interesting, recently there being a white paper, the report, quantum simulation for high energy physics. So there have been a lot of interesting application in quantum computing in the physics problem domain. So why are we interested in quantum computing? So let me just quote the sentence from Richard Feynman. Nature is not classical. And if you want to make a simulation of nature, you better make it quantum mechanical. So many problems are inherently quantum mechanical. So like everything just in this room, like this, the cell phone you're using, right? What's inside it is more or less quantum mechanical. There's vast amount of resources, vast amount of encoded information that can be put in a many-qubit state, which is not possible to do it with a classical bit. And nature does this for us automatically. So it's our purpose to use it, to take advantage of it. And what's more, there's a high scalability in quantum applications with efficient encoding, as you can see already in many problems. And we have a rapid progress in hardware, software, and algorithm, as I mentioned previously. And this is the road to quantum computer. And currently we are here. And it's a logarithmic road. So where you can see the first quantum computer version of the ENIAC machine would be around here. So we're very far away. But during this road, there are specific problems that we can solve. So it's very important that we push toward that in the future. And now, so my lecture is meant to give you an introduction to quantum computer. So I will just, so everything about my talk will be focused on this slide. So on the one hand, we have classical computer, where you use a classical bit, as you may already know. So it's also called state. So you could have either a 0 or 1 to represent the state, like a classical bit. Just think of this as a switch, as you can see, just on the wall, right? You can turn on and off. There are only two possibilities. And for a classical computer, you need classical gates and or not, or bitwise gates. Those are, if there's some engineering, you're probably familiar with this. And it has a deterministic nature to the classical computer. But on the other hand, quantum computer, the information is encoded in the quantum bit, and we always call it as the qubit. It's a nomenclature, and it's basically a two-level quantum system. So instead of thinking about it as a switch, now you have something like a ping pong ball, right? And then ping pong ball also have two ends, right? But you can also have a point to any direction on the surface of the ball. So that's basically what a qubit is, by drawing an analogy. And the quantum gates are different. They are unitary operators, which I will introduce later. And the quantum computer has this unique feature that allows for superposition, probably already know, and then entanglement. And like a recent Nobel Prize is about entanglement. And it has also this very different quantum behavior that state will collapse when you do the measurements, which is not presented in a classical computer. So my following slide will be focused on these highlighted keywords. And to describe a qubit, we will introduce a bra-ket notation. So the qubit or quantum bit can be in a superposition of 0 or 1. So basically any other place on the ping pong ball. So it's a vector in the two-dimensional complex vector space, strictly speaking. And to present the quantum state of qubit, we introduce a bra-ket notation, or the direct notation, invented in 1939. The ket is basically a column vector. And the two states that I showed previously, 0 and 1, can be represented as these two column vectors. They will form the basis for our single qubit. And so the quantum state can be a superposition. So we can write the wave function or the state of the qubit as a superposition, a linear combination with coefficient alpha and beta, where alpha and beta are complex in nature and their norm squared sum up to 1. And on the other hand, we also have the bra notation, which denotes a row vector. So currently, just think about it as a row vector. It's also called an adjoint vector of the bra. So basically, you just lie down, you calculate the transverse of those column vector, you get those bras. And similarly, you can also describe the whole system by converting the ket to bra. But in the process, you also need to make the coefficient complex conjugate. So this is a very short introduction to bra-ket notation. So I put this exercise here to help you. So the bra-ket can be calculated as a complex matrix multiplication. So think about how do you evaluate those brackets. So take like 2 or 3 minutes to think about how you calculate them. Just let me know if any questions. I can do the first for you. So as I said, this one will be a column vector, and this is a row vector. So simple matrix multiply. So this number multiplied by this, plus this number multiplied by this. So 1 times 1 plus 0 times 0. That gives you 1, right? So you can do the same thing for the other brackets here. So what do you think would be the value for this one, for example? Any guess?
0.
Yes, yeah, that's a 0. And what about this? This way, you probably need to write it out and see it. And what about the last one? If you do not do the calculation, what do you think about the last one? Guess? 1. Yes, that should be 1, right? Because it should be normalized, right? So I'll just show you the result. So as we already did the first one, and second one is 0 because if you put them together, 0 plus 0 give you 0. So these basically tell you 0 and 1, they form also normal basis. And this one, so basically, so here you have to solve it linearly. So you have to separate out because it's a, I don't know I can do that. We have to separate out as linear combination, use the linearity of the superposition. And then this first term give you 0, give you 1. And so you got an alpha. The next term give you 0 because you already proved here. So in total, it just give you alpha. So basically, this helps you project your psi into this basis. So you grab your coefficient from this basis, right? So it's very intuitive. It's basically projection. And last one, if you do the calculation, you will see that it will give you the alpha squared plus beta squared, which is by definition 1 because the function has to be normalized. So just some footnote, this bracket forms the inner product on the vector space. So it's related to the quantum measurements. And you probably heard of Hilbert space, this term a lot. It's basically a complex vector space with this inner product rule. And alternatively, so we could use this bra-ket notation. It's very fancy. It's very neat. But you could also describe everything on the ping pong ball using the Bloch sphere visualization. So basically, you build a parameterized function for the 0 and 1, and then you can map the parameter on the ping pong ball. So normally people use this Bloch sphere to represent the ping pong. So, and then the theta would be this vertical angle, and the phi will be the transverse angle. Sometimes also referred to as the relative phase angle. So you have this X, Y, Z representation, right? And there are many popular states besides this 0 and 1. You also have this plus state, which is actually just a 0 state plus a 1 state. So that's very, very commonly used. And it's basically the even superposition of those two basis states. You have this minus state, which is 0 minus 1 divided by the square root of 2. Okay, so you will see this a lot in today's exercise. And psi can also be represented not in this two bases. You could also represent it with the plus and minus basis. So it doesn't matter which basis you choose.
That's true.
Yes.
Can I ask a question?
Yes. Yes.
In the last slide, the coefficient in front of the minus, should that be alpha minus?
Thank you. Thank you. Sorry, this is a type. This should be a minus. Right? Alpha minus. Otherwise, it will be weird for any arbitrary sign. Yeah. Thank you. Yeah, and okay, then we talk about the qubits, and now we want to look at quantum gates. So quantum gates are what we use to modify the state of the qubit, as you can see here. So this is I use the quantum circuit here, but you can see Q is like a qubit, and you apply a sequence of gates to this qubit to modify its content. And the unitary operators are operators on the hyperspace that preserve the inner product. So this is very important to remember that no matter what you do to the qubit, it should still be normalized all the time. So that means all your operators should preserve that product. And you can write them as unitary matrices. That's what we will be dealing with today. And they have to satisfy unitarity. But for now, just remember, all quantum gates must be unitary, meaning preserving the probability. And unitary operators, any unitary operator is a valid quantum gate. And this is very different from classical gates. Imagine if you have a classical AND gate, AND gate, and you 0 and 1 will give you 0, right? But from 0, you will not know what you begin with. But that's so in that sense, you destroy the unitarity. So that's entirely different. This is a quantum thing. So the byproduct is that you have many non-trivial single qubit gates, such as the X gate, Z gate, Hadamard gate, and the phase gate. So those four are the most common single qubit gate. And we still do the same thing, multiply them as matrix on the state. So I will introduce those four because they are very common. The X in the matrix form is written as this. And what you can see, basically swap the content of those two bases. And if you just look at the 0 and 1, it changes 0 to 1 and changes 1 to 0. So in quantum computing, people also call this X gate the quantum NOT gate because it negates the content of the qubit. And the Z gate is referring to the poly Z gate. And you can see it basically icon 0 give you 0, and icon 1 give you a -1. It is a diagonal, so you can see why this is happening. And then you also have this Hadamard gate. This is the very strange looking gate. But what it does is basically map the 0 to the plus gate and map 1 to the minus gate. So Hadamard basically map your 0 to here and map your 1 to the minus gate. So it's very, very good gate because it can change your computational basis. And it's very widely used. And lastly, the P gate basically apply transverse relative phase to your qubit. And it's important to know that all these are reversible, meaning every one of these matrices will have are invertible, so they have inverses. So if you want to get the initial state, you just need to multiply by the inverse matrix on the final state, you will get initial state. And that is a very, very quantum thing to do. And we have looked at single qubit state. The next thing will be to look at multi-qubit states. So like you have this two circuit here. And the quantum advantage lies in multi-qubit state because, as I mentioned at the beginning, the advantage lies in many body system. The quantum so these two, I guess okay, I'll introduce this first. So the quantum controlled NOT gate, sometimes called C0 gate or CX gate, is the most useful 2-qubit gate. It acts on 2 qubits, A and B, where A is a control and B is a target qubit. If the control is 1, the C0 gate will replace the value, negate the value of the target qubit. So it is the simplest form of quantum entanglement. So as you can see here, the signal gate applied on qubit A and B. And if A is 0, it doesn't do anything to B. Similar here and here. But if A is 1, it negates the content of B from 0 to 1 to from 1 to 0. And the matrix form will be of the following. Sort of, you can guess that, why these two are swapped. So it will be an interesting exercise to write out the quantum state for those two circuits above here.
Excuse me, can you repeat the explanation of the 00 arrow 0001?
Yeah, sure. So I want to apply the signal gate on qubit A and B, and A is the first number, and B is the second number. Because my control is on the first number, so I do not do anything to B unless the first number is 1. So you can see if it's 0, then the content remains the same after the signal. Similar here and similar here. But if the content is 1, I will change the content of the second one. Okay. As you can see here. Yeah. Okay, thank you. Yeah. So back to the quantum circuit above. So think, how would you calculate the quantum state after the circuit? How much time do I have left? Okay, I should probably hurry up. So basically, so in notation here, the first one is always on qubit 0, and this one called qubit 1. So you apply a Hadamard on qubit 0 with the 0 here, and apply an X on qubit 1. So this part basically signifies what this circle means. So then you can apply them separately on different qubits. So just distribute it on the qubit, and Hadamard will give you a plus state, and X will negate the content to give you 1. And in the end, you can choose to recombine them. So that's what you get in the end. But if you have a CNOT, this will be more complicated. But the idea is the same. You apply the matrices on the content, and in the end, you get something like this. And it's very important to see that this state is not separable. You cannot write this state as a product of two states. And so that's the idea of an entangled state. So those two states are entangled. So so basically here is a Bell state. So in a everyday language, you can say that if you know the state of the first qubit is 0, the second one must be 0. If you know the state of the first qubit is 1, the second must be 1. It's like you and your friend living very far away. You each have an apple. If you taste the apple to be good, and that friend can know that her apple is tasty without even eating it, right? And if you know it's bad, then her apple will be bad too without eating it. So that's basically the idea. Okay. So, and then I introduced the quantum circuit in the process. But you don't have initialization, but we did look at the quantum gate. So the other important thing is measurements. So we are all good writing all those algebras, but those are not what observed in experiment. In experiment, we have to measure in order to know the content of the qubit. It's not like a classical computer, the number just revealed itself. For quantum mechanics, it's hidden in the state, so you have to measure it. So this is the notation. So each horizontal line, as you see across the screen, like Q0 and the horizontal line, represent the evolution of a qubit from left to right. And each measurement represented by this funny little symbol, which you will see a lot, collapses the wave function. So, and then we will obtain either 0 or 1 in the respective computational basis. And usually by 0 and 1, it's already in the vertical basis. So the bra-ket 0 and 1 basis. So in practice, so you imagine this. So you run the circle once, I got 0 and 0. But remember, we should expect to see this, right? So what is happening? We did not get 1, 1. Right? So the issue is that what this expression means is that you have 50% of chance getting 0, 0, and the other 50% of chance getting 1, 1. So you cannot achieve this in just one run. So you have to repeat this many, many times, as many as possible. So when you have enough number of repetition of the circuit, if you run this enough many of measurements, you will get even distribution of your final result, as represented in the histogram here. So this histogram is repeated for 1024 times of the circuit. So sometimes people also call this as shots. It's like, yeah. So that's a basic idea. So your measurement as a statistical outcome are running a circuit repeatedly. And now today we're here because the Qiskit, it's a Qiskit event, right? So I will introduce a Qiskit library. It's called Qiskit. It's an open source software for quantum computing framework. It's very versatile. It can be worked on the quantum process, the quantum circuit, as we focus primarily today, and also application modulars. So this is from the pulse, to the circuit, to the transpilation, to the quantum hardware geometry, to different applications such as this one is the max cut problem, and to actual quantum machines. So it has been a lot of application in natural science, optimization, quantum machine learning, and finances. And particularly Qiskit, unlike other software I introduced, it gives a unique access to quantum backends, including cloud computer that we can use without paying, and also noise simulations. So I will introduce several libraries here, which will be useful for today's challenge. So you can also refer to those slides when you do the challenge. So the operational flow library basically does all these bra-ket calculation for you on the quantum computer. So these are just languages in Qiskit. You represent 0 as 0, 1 as 1, plus as plus. Remember those bracket notation, and the gates can be represented also very easily. And you can have like a single qubit state constructed using those languages, and it's also multi-qubit state constructed using the caret symbol here. And also you can build superposition just as you would write a sentence. And also the gate can be composited, and you can evaluate the expectation value. And these are already available on GitHub. And the other library I want to introduce is quantum circuit, which Juan will introduce in the next hour. Basically, circuit is a fundamental element for quantum computing. In Qiskit, it's represented by this circuit library. And this object called quantum circuit object, which you will memorize today by the end, is using everything. And from Qiskit, import quantum circuit. So all these are in Python. And the beauty of quantum circuit, you need 3 qubits, so just put a 3 there. And you want to put a H gate, which is a Hadamard gate, on the 0th qubit. So I still like to point with something. Yeah. So I like the old-fashioned way. So this is your circuit you want to build. Put a Hadamard on the 0, so just write H on 0. The qubit is optional, just help you to understand. And you want to put a control X, that is a control on Q0 and acting on Q1. So, and then you put a 0 and a 1. And then you want to put a control on the 0th qubit and acting on 2. So just 0 and 2. And then measure all would represent all these black measurement symbol here. And then you draw the graph. Right. So with a few lines, you can fully represent the circle. So it's very convenient. And you will have a lot of practice today, so you should learn how to do this at the end. And the other thing is that we have to run the circuit many times. So the AI library give us the backend or the device simulator to run the circuit, and you can pick different backend. So these two backend are the most important. The first one is the exact simulation, and second one give you a statistical outcome, as you can see in the previous one, the histogram. And these are the languages to do that. It's very reader friendly. You run the circuit, you execute, and then you get a job, and you get the counts, and then it's represented as you get 111 state 542 times out of 1024 times. So it's very semantic. As you can see, you can increase this SHA so you get closer distribution as you expected. And then you can visualize the counts that I just showed you with a single line, plot, histogram, counts, and add your favorite title, and you get what is presented. As you increase the number of shots, you will get an even distribution. So that is what we expect. So from this histogram, you should know that the quantum state you get in the end is superposition, even superposition of 0, 0, 0, and 1, 1, 1. And so I finished my lecture here, but I will talk about quantum computing in the near future and pointing to my organizers. So there are several directions for quantum computing in the future. One is the variational approach. This is currently the predominantly publication in quantum computing is about variational approach. So you have this variational quantum eigensolver or VQE, and it's a hybrid optimization. So you put some of the calculation on quantum computer and some of the optimization on classical computer, and then you let them talk to each other back and forth. And when you let them run enough time, they will produce an optimal outcome. And in some application, it's even better than current result in just using classical computer, especially in chemistry, because you have many molecules. It's very much many body problem. And on the other hand, we have this decompositional approach where you do not rely on quantum computer. You just run the circuit once, right? So you can do different optimization to this Hamiltonian evolution, as Mijia will introduce today. And then you will get a result that you can measure. And also, there's also, of course, quantum computing algorithms that are being developed. And so I'll let Juan to talk about it in the next hour. So, and okay, and I also want to point this thing, the IBM Quantum public backend, which I think is separate Qiskit from other framework, because you have direct access to real quantum computer. So here I just make a screenshot of the quantum computer that is available when you sign in on your IBM account. So it's a Nairobi quantum computer. It has 7 qubits, 32 quantum volume, and calculation speed, etc. And but this is a real quantum computer, but it's not as perfect as this ping pong ball. So the real quantum computer nowadays is like a dented ping pong ball, like that, because you have C0 error. So the gates are not perfect. Yeah, you have this readout error. If you read out something, it's actually not that same. So it's you can see that if it's a perfect readout, it will be a diagonal thing, but you can see it's not. And their relaxation time, that means you must finish your job in this time, otherwise it's totally wrong. Okay, so there's a lot of errors, but this is toward the public backend to be used in the future. Just be positive, because you know, the company actually has planned out their development in the next 2 years, maybe more. So we already have this 127 qubits. Although it's not public, but it's commercially available, and there will be application modulars added to the framework, so people can use it without understanding quantum computer and by getting the benefits of using quantum computer. So and this is the real quantum computer, and that's the end of my talk. So I put this on the last page. If you are interested in knowing more, those are the few places you should look first. The Qiskit Online textbook is very well written, and if you want to know the physics more, you should read this the Chance and Nielsen's book on quantum computing. And then if you like today's challenge, which will happen in 2 hours, you should sign up for the IBM Quantum challenge. It's more official than us and much harder if you are interested in knowing more. Okay, so I have some minutes left. So if there are any questions, I can take to answer.
Well, I have a question.
Yes.
How do you implement quantum gate as X-ray
That's
physical?
That's a very hard question for me. For what I know, I can answer is that on different. So you're talking about this Qiskit, right? So on different quantum computer, this Qiskit is implemented differently. On the supercomputer, they probably new super conducting ion computer, they probably send different microwave to the qubits so that to change its orientation and stuff. So it's known for the engineers beforehand, and we here just call it. And for like a photon computers, it's done different. You have to change the polarity of the photon in some way. So it's more on engineering hardware level. Yes.
Another is what physical system is the qubits in practice?
So it's also depend on different hardware. So if it's a photon computer, the basic qubit is a photon. And if it's a computer used by IBM, it's basically ion. And they are just basically any two-level system can be used as a quantum computer in theory. But some are still have some advantage in some area, a disadvantage in some other area. There's no perfect quantum computer nowadays. So people are still racing to find what's the best system. Yeah.
Thank you very much.
It also depends on the application. Like for communication, it's better to use photons because they can travel distances without, like you can send them, but you cannot send superconducting tube. It's very good.
So for communication, probably better to use the phone.
Yeah, as far as I'm concerned.
Yeah.
They can use some other thing.
Let's hope to give some introduction to the material. Don't get too intimidated by this, because today you will be working on the code, so maybe these are looking more friendly to you.
When we are running the code on the computer, on our computer, what we do is on the quantum simulator, not the actual quantum computer.
Yes, but as I said, anyone can log into your IBM account and use this. So it's publicly available. So as you can imagine, when you run this, you have to wait for other people to finish their job. So sometimes you see, I run already 2,000 jobs already. Sometimes I have to wait for a whole day to run my job. So that's a disadvantage. But you can buy commercial IBM quantum computer to do your research. I think it's totally possible.
How expensive are they?
They are quite expensive. I think, and I remember €1 per second for execution time. For 1 second execution time. So, but if you have this thing you want to do very much and it doesn't take much time, you should do it. $500 maybe will help you publish your results. Because as you can imagine, those computers are much better quality than the public ones.
Also, the execution time for a circuit is not that long because, as you saw before, like there, like at the current times, the current times are for milliseconds, microseconds. So you have to run several circuits to get to 1 second.
Yeah. So you shouldn't doing too complicated calculation with this backend, basically. Yeah. Any last questions?
The relaxation time and the fixing time, what are they exactly?
Yes, so I'm not an expert, so I wrote a hint for myself. So T1 relaxation time means your qubit is originally in the up direction, and then you apply an X gate, it will be the down direction. But over time, it will slowly go back to the 0 direction if you just let it hang there. This is, I think, the mean time for it to go back to the 0 direction. So this, if you know about the medical instrument, it's like MRR thing, basically. And the T2 deflating time is similar. If you set your qubit to the plus direction, the X direction, it will slowly deflate to the minus direction. Yeah. It's like the half time for the qubit stability. That's a way to think about it. Any more questions, or we can move on to the second lecture? Or do you need some 5 minutes break? 5 minutes break. Okay. Yes, we're waiting. Yeah, just feel free to ask a question during the break if you like.
No tenéis que estar esperando de nada, ¿no? Es que yo estaba pensando, ay, qué bien me ha venido tener álgebra 1.
Y la parte matemática.
¿Qué?
La parte matemática perdí muchísimo.
Yo lo estaba pensando, pero yo eso lo di en primero, lo del bra-ket, lo de la notación de Dirac. Yo lo di en primero así un poco. Pero luego te lo dan por sentado. Ay, supongo que os lo enseñarán. Es una forma, es que Dirac se creía guay. Entonces dijo, voy a crear mi forma de escribirlo. O sea, literalmente.
Igual te estás sonriendo mucho, o sea, que estás emocionado. El de negado calculado lo vimos en tecnología el año pasado. Ay, yo estaba diciendo, coño, esto creo que lo daba. Es que esto lo vimos. Bueno, tú lo diste en tecnología. Bueno. En TIC, ¿no? En tecnología. ¿Qué tal?